Alright, so we're starting with number 5 here. Common uncharacteristic state of the moon orbits the Earth, which creates the image of the moon's orbit shown in this. Gravity pulls on the moon, causing it to orbit, yes. No, okay. This problem will calculate the location of the center mass of the Earth-Moon system. Then it will calculate the center mass of the Earth-Moon-Sun system. And it gives us the mass of the moon, the mass of the Earth, the mass of the sun, from the distance from Earth, Moon, and Earth is this. The distance from Earth and Sun is this. Alright? Worth x0, and the moon is located in the positive x direction. And then let's view all hidden parts here. And then calculate location of center moon during a full moon. The full moon occurs when the Earth, Moon, and Sun are lined up as shown in the figure. Alright. So we're going to have to do 2 diagrams here for our center of mass problem. Alright. So we'll go here, and then I'll pick a center of mass diagram. Remember, the things I'm doing in here is I'm looking for the situation correctly, all the locations and diagrams, masses or forces shown incorrect, and labels on diagrams, easy to understand. So I'm going to do 2 diagrams here. We'll do Earth and Moon, and I'm going to draw them kind of like dumbbells, just because I feel like doing that. And then the second one I'm going to need is going to be Moon, Earth, Sun. So I'll do that down here. Moon, Earth, Sun. Of course, not drawn to scale. And let's see, they told me, I think, oops, scroll here a little bit. Got to get all my information in there. So, which the center of the Earth is at x equals 0. The moon is located in positive x direction. So, I'm going to say that this is 0 here. And then this would be the mass of the Earth. This would be the mass of the moon. This would be our Earth, Moon. Where do I think the center of mass is going to be in that? Where do I guess? Close to the Earth. Like here? Yeah. And that's really just a guess, right? What do you guys want to use as our point of reference, where we're going to measure all our distances from, things like that? The Earth. And that's good because they told us to put the Earth at 0, right? Okay, so our point of reference is going to be the Earth right there. Alright, so that would be good for my diagram for the first part. My diagram for the second part, similar. Set, let's see. In which the center of the sun is at x equals 0. Okay, so they want me on this one to put my point of reference here and to call this direction positive. Right? We can do that, right? And so other labels I would have in here would be mass of the Earth here. Oh, sorry, mass of the moon there. There we go. Moon, mass of the Earth, mass of the sun. Where do we think our center of mass will be? So you tell me where to stop. Right here? Okay. I could probably label that as CM, right? Just to clarify. And then we'll have, let's see, from here to here would be radius of Earth to Moon. Here to here would be radius of Earth to Sun. Is everything clear to understand? Can I hit that point on the rubric? I think so. At least I understand it. Is it clear to you guys? Yeah. Okay. All right. So I think I hit all my rubric points. Now go down here to our how, and I need my center of mass equation, and I unfortunately forgot to open up my equation sheet, but I remember it off the top of my head, which is XCM equals M1 X1 plus M2 X2 plus plus M to the N X to the N all over mass total. One way to write that. Right? How many masses do I have in part A? How many things do I have in the first part? 2. The Earth and the Moon. So I only need 2 terms in this. Okay? So now I'm going to plug in XCM. So that I don't know. I don't know how far the center of mass is from my reference point. This will be the mass of the Earth. And then how far the center of mass of the Earth is from my reference point. So I go back up to my diagram. How far is the center of mass of the Earth? How far is the Earth from my reference point? Remember, my reference point is the big red dot. It's 0. So this is times 0 plus mass of the Moon times, and that would be the radius from the Earth to the Moon away. So radius Earth to Moon all over mass of the Earth plus mass of the Moon. All right? Any questions on me setting up the equation for the first part? So XCM is what I'm going to solve for, so I'll leave that as a variable. Mass of the Earth times 0 is what? 0, right? So can I just leave that term out? Make my life easier? Mass of the Moon, they tell me that. There it is. They tell me mass of the Moon is 7.35 times 10 to the 22nd kilograms. So 7.35? Definitely having a Friday brain. 35 times 10 to the 22nd kilograms times radius from Earth to Moon. The percentage distance between the Moon and the Earth is 3.8 times 10 to the 5th kilometers. And they want my answer in kilometers, so I'm not going to change that to meters. I'm going to leave it as kilometers. All right? Earth to Moon, 3.8 times 10 to the 5th. 3.80 times 10 to the 5th kilometers. All over mass of the Earth, 6.00 times 10 to the 24th kilograms. plus 7.35 times 10 to the 22nd. And then I just use my calculator for what it's made for, right? Is that good? Let's do part B then. So in part B, how many items in part B? 3 things. So I need my equation to have 3 terms. XCM, we're going to have mass of the Earth, radius Earth to Sun, actually, mass of the Earth, location of the Earth, plus mass of the Moon, location of the Moon, plus mass of the Sun, location of the Sun, all over mass of the Earth, plus mass of the Moon, plus mass of the Sun. Good? All right. Now I'm plugging in again. I need to, though, keep in mind that the Moon, it goes Moon, Earth, Sun. So, like, the radius from the Sun to the Earth is 1, and then the radius from the Sun to the Moon is going to be those 2 radii combined. So, equals mass of the Earth, that was 6.4. So 6.00 times 10 to the 24th kilograms. Location of the Earth from the Sun is that Earth to Sun radius, which is 1.5 times 10 to the 6th kilometers, so 1.5 million. So 1.50 times 10 to the 6 kilometers, plus the mass of the Moon, 7.35, 10 to the 22nd kilometers, and I'm going to run out of room again. And now, this is the tricky one because I need to add together the radius from the Earth to the Sun and also the radius from the Earth to the Moon to get the radius of the Moon to the Sun. And so I add 3.8 times 10 to the 5th kilometers plus 6.0 times 10, oops, plus 1.5 times 10 to the 6th kilometers, plus mass of the Sun, 2 times 10 to the 30th. Wow, that's a huge number compared to the other ones. Kilograms. Times 0 because it's 0 away from its own center. And now I just bring down my 3 masses like I did before. Right? I need to learn how to write smaller. Are you asking me a question? Sorry, I can't.
Yeah, well, it's actually 3.8.
1.5 times 10 to the 6th kilometers. And now it's all numbers. Maybe I can do I'll write that one again. There we go. Good? On number 5? All right, so number 9 here. Number 9, radius of Mercury is this. Acceleration of gravity on a surface is this. What is the mass of Mercury? So this is going to be a general line, right? And we're looking at number 9. So what affects the gravitational field strength? Mass of the object. So does more mass increase it or decrease it? Increase it. So the more mass Merc has, the stronger the field. What else influences gravity? Distance. So if you're at the surface of a planet, what distance matters? Where are you comparing where you are to? The center of it, right? So, and if the planet has a bigger radius, does that increase or decrease the gravitational field? Decreasing it, yeah. The larger the radius, the less strong the field. I think that's probably enough. You've shown you understand that it's the mass and the radius of the planet that are influencing this, and how those influences are affecting it. Radius, I'm going to say of Merc. Cool. All right. Let's go on to the how. So if I go up to my equation sheet and I look in the forces and gravity section, because it's about gravity, and I've got the gravitational field strength of a planet is universal gravitational constant, big G, mass of that planet divided by the radius of that planet squared. So that's the equation I'm going to use. I'm going to copy that down. And they wanted me to find the mass of Mercury. So I'm actually going to, before I do anything, I'm going to rearrange so I have mass of Mercury by itself before I put in anything. So just a little bit of algebra, radius of the planet squared, gravitational field strength. Actually, I'm going to make that the radius of Mercury. Gravitational field strength on Mercury all over big G equals the mass of Mercury. Just a little bit of algebra, right? And then just plug in. They give you the radius. They give you the little g. You know big G. Where can you find big G? Any reference sheet or anything you have that might have the universal gravitational constant on it? Huh? Yes. Yes, there is one. And then you just, so you have all three things on the left side. You want the thing on the right side. Happy days. Yay. Alrighty, so on to number 8. The gravitational force between two volleyball players is this. Mass of the players are these. What is their separation? Okay, so it's a gravity problem. So we're using our general template here. I could include a diagram here, maybe. One volleyball player, other volleyball player, and which way is the gravitational force going to be on each of those? Down? I don't think so. Why would it be down? But it doesn't say they're on the Earth. But let's assume they are. We're interested in the gravitational attraction between them. So how much they're attracted to each other. So is that force going to be pulling them down? No, it's going to be pulling them together. How much their attraction to the Earth is pulling them down. So they're both, and what do we know about those two gravitational forces? They're equal, because all forces come in pairs. So I might write things like they are gravitationally attracted to each other. What contributes, or what contributes to that attraction? The mass. So both players' mass, right? Maybe it's a good way to say it. Both. Masses. Contribute. I'm being lazy and abbreviating. How far apart they are. Oops. Also that's kind of it, right? Those are the factors that are going to go in here. We could also say, hey, whatever universe they're in will contribute to it. But given that there's only one universe, right? Right, yeah. Otherwise, it wouldn't be called a universe, it'd be called a multiverse, yeah. Alright. Now we need to pick out our equation. And since it's about gravitational force, I'm led to use the gravitational force equation. Kind of makes sense, right? So squared, I know big G is 6.67 and 11 Newton meters squared per kilogram squared. One reason I always put my units on my universal gravitational constant is to remind myself that to figure this out in newtons, I've got to have a radius in meters, I've got to have both my masses in kilograms. So that's one of the reasons it's great practice to include units and everything. And now it's just substituting in, right? I know big G. They tell me M1, 63 kilograms. They tell me M2, 73 kilograms. They tell me the force, and so the only thing I'm left with is the radius. I know everything else. So substituting in 3.7. -7 newtons equals, substitute big G. For me, it's 63 kilograms times 73 kilograms salt per. How many sig figs should I keep R in? 3, always 3. A lot of points given away on the last test. That way. Should have left hand.